So I'm Jim Kitchen. Sorry for my voice. I'm a little under the weather right now, but I work at Anaconda. Erik is over at NVIDIA, and we've worked together in the past. And the third presenter, Imriddle Seth, he's one of the core developers at NetworkX. His internet's a little spotty today, so I'll just be presenting for him instead. But we wanted to talk about making NetworkX faster, specifically 100 or more times faster, with a feature called dispatching to GraphBLAS, and we'll get into that in a bit. So first of all, just to sort of set the minimum foundation of why graphs are important. First of all, if I assume everyone knows about social networks like Facebook and Twitter, where each person is a node in the graph, and the connections between them are like Facebook friends or Twitter followers, other social connections. Graphs can also be used for route planning, where intersections are the nodes, and then the actual roads form the connections. And sometimes roads, only go one way or have a speed limit. But with those, you can use graph algorithms to do route planning, for instance, and make Google Maps work. Sometimes in tables, you have hierarchical relationships where you have a many-to-one, like who is my employer? And what you find is, while SQL and others can handle things like that, it's tricky when you don't know how many levels deep you need to go. Question like how many employees are in Jeanette's organization? You don't know how many times you need to join the table to itself to answer that. So framing that as a graph problem is usually the right way to go. So that's just basic of why graphs are important and why people care about them. Today, we're specifically talking about NetworkX, which is an amazing library. It's the most popular graph and network library in Python. And if I had to pick a superhero for NetworkX, I would pick Spider-Man. He shoots webs. It feels appropriate. And of course, Spider-Man is amazing, and so is NetworkX. And let me talk about the ways that NetworkX is amazing. First of all, it's amazingly easy to use. It's a pure Python package. It has easily understandable object model, so just dictionary of dictionaries, a nice stable API. It's amazingly well documented. If you go to networkx.org, it's got tutorials, introductory materials, a gallery, educational notebooks, all kind of good stuff. It's amazingly easy to contribute to. So it's got a developer guide, a very friendly community, and the source code is very readable. So it's easy for someone who's more on the academic side to come in and start contributing. It's amazingly flexible. Anything that is hashable can be used as a node in the graph. You can add multiple properties to nodes or edges. Some might say it's a little too flexible, but for now, this is a good power. And of course, it's amazingly slow for large graphs. This is why the talk comes. This is known for a long time. Anytime you're iterating with Python for loops over dictionary of dictionaries, it's going to be slow. So the question is there a way we could solve that last problem to keep NetworkX amazing? So what are potential solutions to this? One is just to wait for hardware to get faster. Moore's law has saved us in the past, but the problem is that data is growing larger at a faster rate than processors are getting faster. So this really is not a solution. Another thing you could do is just try to rewrite everything, right? Throw it all away, start, go down to a bat cave, hire Lucius Fox as a genius and write some, C++ or Rust graph library. And these have been done. The problem with this approach, though, is that you basically lose the community. You lose all those other amazing aspects of NetworkX. So we don't really want to go this route. Instead, our proposal is a thing called dispatching, which I think, most easily explained is, Spider-Man is great around New York City. He can sling his webs and swing between buildings. He's great. But as soon as your graphs grow to the size of like the United States, having Spider-Man just running through Kansas is really slow. He needs to instead catch a ride on a bullet train or something. And so this is our approach, is having users still interact with Spider-Man, right, with NetworkX, but add extra capabilities where Spider-Man can now catch rides on faster libraries, on bullet trains, if you will. All right, so the vision here is NetworkX both as a reference implementation and also as an API. So if we step back and just look at Python has its own superpowers. Why is it the number one thing for machine learning and AI and other things? It's because it has a very nice API that users like interacting with. But library authors go a lot deeper. They go into compiled libraries, they add bindings and expose the API, but the users of those libraries don't ever have to dig into that, right? You can use TensorFlow without knowing C++. And that's a superpower. if we look at one of the biggest success stories in Python, NumPy, NumPy wraps a lot of C code, Fortran, it has Python and other things. But when you just install NumPy and use it, you don't have to care about that. It just works. And so NumPy is a very nice interface. It has exposed an array interface to actually let other objects masquerade as NumPy objects. And in fact, other array libraries like Dask.array and CuPy wrap their own set of different things and have sort of mimicked the NumPy API. So while NumPy is both an implementation, it also has sort of become this API. And the question is, can we do the same with NetworkX? Right? NetworkX is both a reference implementation that's just fine for small graphs. But it's also then an API, right? We've got this API layer here that you call into, but when you call into it, it could dispatch to the normal NetworkX, but could it dispatch to other things, right? SciPy sparse, GraphBLAS, cuGraph. And the interesting thing is, if you look at NetworkX today, this is what's already happening. Like NetworkX internally is already doing some dispatching. For example, PageRank, the pure NetworkX version is too slow. So when you call PageRank with NetworkX, it will take your NetworkX graph, translate it to a SciPy sparse adjacency matrix, and then call the version using SciPy. And it's faster to do that, to pay that translation cost and run the SciPy than it is to run the NetworkX. So this is already happening a little bit. We just want to expand that with the plugin architecture and let other libraries plug into NetworkX. So let's look at this in a practical sense. A dispatching example with GraphBLAS algorithms. So first of all, this is what the NetworkX looks like. You import NetworkX, we're going to make a random graph with 8,000 nodes, about 640,000 edges, and we're going to run the K-truss algorithm on it. In this case, the 5 truss. And on my laptop, this takes about almost 11 seconds. Okay, if we make 2 small changes, so we import GraphBLAS algorithms, and then we make a new object G2 where we just say, hey, I want to make a GraphBLAS algorithm graph from the NetworkX so that it does the translation. And then the interesting thing is we pass that G2 object directly to the K-truss of the NetworkX. And the translation takes half a second, but running the GraphBLAS version of K-truss takes a quarter of a second. So, if we ignore the translation cost, that's a 40x speed up. If you include the translation cost, that's still more than a 10x speed up for a graph that's honestly not that big. One thing to note is that this dispatching is purely opt-in, right? We had to specifically pass G2 into the NetworkX K-truss algorithm. Now you might be wondering, how does this magic happen? So let's look behind the curtain. This might be a little small on your screen. I apologize for that, but here, this is the NetworkX K-truss algorithm. And in the 3.0 code base of NetworkX, there's a new nx._dispatch decorator that some of the algorithms have been decorated with. What happens is when you call this, it first looks at that G parameter and says, do you have a Dunder NetworkX plugin attribute? In our case, where we passed in G2, yes, it does. And it would respond GraphBLAS. So then it'll go and use the Python entry points mechanism to dig down, find the GraphBLAS interface. It'll load that up and then call its K-truss implementation. And if you aren't familiar with entry points, this is a mechanism within Python that lets you register at the environment level so that you can query different packages, metadata, without actually importing the data. And only once you find the right thing that you want, you call .load. And here, this is GraphBLAS algorithm setup.py, where we've registered this entry point. And so when we call .load here, it actually goes and grabs and imports this library in this specific class, returns it here as GB interface, and then we can interact with it. So one thing to note is that not all of the NetworkX algorithms are decorated at this point. This is still a little experimental of a feature. If you want to find out, you can use that to see which algorithm decorated. Hopefully we'll have a better mechanism in the future. It's kind of ugly for now. All right, but if we keep looking, this plugin interface class, what does it have to do? If you were a library author, what would you have to provide? Really, there's 3 things you need. First of all is you need a way you have to have a function with matching signature for each of the decorated NetworkX algorithms that your plugin is going to support. So in our case, we have this dispatcher class, and the actual implementations can live somewhere else. We just have this place as sort of a namespace where we pull them all in. And that way you can call nx.any of these and it'll go to our specific implementation. There's two other pieces. You need a convert from NX and a convert to NX method. And what these are doing is that we added a feature where we wanted our plugins to be able to verify that they're working correctly, that they have, feature parity and, both in signature and in behavior with the original NetworkX implementation. So what you could do is you could actually run the NetworkX tests here, but as long as you export an environment variable, NetworkX graph convert, in our case, we set equal to GraphBLAS. If you set that right before you run your NetworkX PyTest, it will run all of the NetworkX tests, but every decorated function, it will go and take the original NetworkX object. It'll run it through your conversion function so that now it's your backend graph object. It'll then, call things, it'll do the dispatch mechanism and then convert your answer back into it so it can actually compare against the original NetworkX tests. So with this mechanism, it lets us use GraphBLAS algorithms. We can run that against all of the NetworkX tests, and therefore we know that we have feature parity with NetworkX. All right, that's a lot already. I'm going to keep diving in. Just a very brief overview of GraphBLAS itself. So GraphBLAS is solving graph algorithms in the language of sparse linear algebra. So there is both a math spec that explains how you take sparse linear algebra. It can actually do graph problems. There is a library called Sweet Sparse GraphBLAS. This was written by Tim Davis, probably the world's foremost expert on sparse linear algebra. It's written in C and OpenMP, a very performant implementation. We had nothing to do with that. Instead, we wrapped it with a library called Python Sweet Sparse GraphBLAS, which takes care of all the CFFI and Cython bindings and that stuff. Then we added a Python GraphBLAS library that's pure Python, and this is sort of where we want users to interact. But to make it really useful, we needed another layer on top, GraphBLAS algorithms, which writes code using Python GraphBLAS, but implements the algorithms from NetworkX and other things. So a couple features about GraphBLAS. Missing values are not necessarily equal to 0. That's maybe a little different from other sparse linear algebra libraries. There's a concept of called semirings, where normally when you're doing matrix multiply and the dot product, you'd find intersecting elements, you multiply them together, and then you reduce using summation. So that's what we call the standard plus times semiring, because you're adding here and multiplying. But you can do other semirings. So when you're doing a dot product, instead you take intersecting elements and you add them together. And then when you reduce them, you find the minimum. And that's called the min plus semiring. Why is that useful? It turns out if you do a bunch of matrix multiplications, you can actually solve the shortest path algorithms using the min plus semiring. So by just adding an extra feature, the rest of linear algebra lets you solve graph problems. It's really cool. There's masking involved. A lot of times in graph problems, you have a frontier that you're walking, so you only care about some of your nodes. And so you can actually pass that frontier in as a mask. And instead of computing everything, it'll just compute the 2 or 3 elements that you're interested in and save a lot of time there. GraphBLAS has lots of internal formats. So the normal CSR, CSC, but there's also doubly compressed and mask dense. I already talked about how this is highly tuned, but it's multi-core with OpenMP. Very performant. It also has connectors to NumPy arrays. So if you want to extract out the pieces of your CSR matrix, you can do that, which lets you translate to other sparse linear libraries. And eventually, this GraphBLAS is going to support GPUs. Okay, with that, I'll turn it over to Erik Welch, who has been doing some fantastic benchmarks to show what kind of performance benefits we can get out of GraphBLAS.
Yeah. Thanks, Jim. I forgot the privilege of talking about benchmarks comparing GraphBLAS and NetworkX. And the numbers shown here are like the speed up you get with a GraphBLAS. So in other words, like the how many times slower NetworkX is. And we build this talk as kind of a 100 times faster version of NetworkX. I think this is a safe claim. Most of these are hundreds of times faster, if not thousands of times faster. So we have the algorithms on the left, the data sets and their sizes on the top, and what I consider like the pain threshold on the right, which is like the typical NetworkX runtimes of the larger graphs that we have here, which are mostly on the right side. So if you have a large graph in NetworkX, you'll typically start by just asking the simplest thing, like get the degree centrality, compute the degrees. And indeed, like this is not that painful. It still takes just about a second. It's virtually in GraphBLAS. But as we increase the complexity even just slightly, like let's get the reciprocity, which asks the questions of how many people do I follow me back? And this takes a matter of minutes in NetworkX, whereas it's like 2,000 times faster in GraphBLAS, which is still instant. If we increase the complexity a little bit more, like, okay, let's look at the degrees of all of my neighbors, or like how popular are my friends? This takes tens of minutes. Like, it's still not that hard of a query. And when we get even K-Trust adds a bit more complexity, and now we're talking about hours. So as you do graphs with these, not really that large graphs, your pain threshold quickly, like your pain quickly increases. The next group of benchmarks do power iterations, and PageRank is the only one of these that where NetworkX first converts it to SciPy sparse, and then computes PageRank with the SciPy sparse. And this conversion is worth it. Like, we get it done in about a minute. But that conversion is not free, and SciPy sparse is still slower than GraphBLAS. And so GraphBLAS is thousands of times faster typically. And as we move down the table, like eigenvector centrality starts taking hours. Cat centrality takes hours to days. So I call that very painful. And like where it gets more painful, like GraphBLAS actually tends to do better because it's multi-threaded. I think the last group is interesting because we are computing triangles and squares. Like, how many like nodes are connected by edges that make the triangle. You might wonder, how do we compute triangles or squares using like matrix multiply primitives? And the answer is cleverly and quickly. So these are like thousands of times, and sometimes like 10,000 or 20 times faster than NetworkX, which starts to get pretty painful. Square clustering, the ones that didn't finish yet, it's still running. Like, these are days into the benchmarks. I'm curious how long it will actually take. And the most painful thing here is the square clustering that hasn't finished yet. In GraphBLAS, most of these take a matter of like seconds, or at worst tens of seconds. But maybe it's not fair to compare against NetworkX because, hey, that's pure Python. So let's compare against a SciPy implementation of PageRank, where it does the same exact computation, just using SciPy sparse arrays, and it's something that SciPy can express well. For the large graphs on the right, you see GraphBLAS, because it's multi-threaded, can still be like 20 times faster, which is significant. But for these data sets, SciPy still only takes, about a second. And as Jim noted with his example earlier, like, these data sets really aren't that large for GraphBLAS. It's like 30 million edges. We can easily do like 100 times larger on a workstation. And basically it's limited by memory. So if you have a beefy workstation, you can go 1,000 times larger. Next slide. Which brings us to cuGraph. If you want superpowers, look no further than Rapids AI, started by NVIDIA. Rapids is a collection of interoperable libraries. Like cuDF is like Pandas, cuML is like scikit-learn, and cuGraph is like NetworkX. And here I'm showing two benchmarks where we run PageRank on a 1.1 trillion edge graph on 2,000 GPUs, and it completes in less than 20 seconds. And Louvain on a 1.1 trillion edge graph on 1,000 GPUs computes in about 5.5 minutes, which is just incredible. So cuGraph, since it's like NetworkX, is a natural library to have as a plugin to NetworkX, and we're excited to do that. A bit more about cuGraph. It does work well on a single GPU and multiple GPUs, and it's targeting GNN workflows. So the cuGraph team is very exciting to make dispatching better for everybody, and to have it dispatch, to the GPU. Off to you, Jim.
Okay, thank you, Erik. All right, with that, we're going to talk about a little bit about the future of dispatching. So just a quick reminder that, right now, well, in NetworkX 3.0, which is still not mainline, but it should be in a couple days, hopefully. Dispatching is currently opt-in. But if we look at the future of what this could be, we want to talk about automatic dispatching. This is similar to what NetworkX is already doing with the SciPy implementation for PageRank, where it takes your NetworkX graph, it automatically converts it to the backend implementation, or the graph type, calls that algorithm, and then converts back. This would require basically zero changes to your code. You would instead just install a plugin in your environment, and things would get faster. This would obviously require estimates of both the conversion time and the algorithm runtime for that plugin, and deciding what happens if I have multiple plugins, right? If I have cuGraph and GraphBLAS algorithms installed, which one has a priority order? Memoizing converted graphs. Today, if you were to call PageRank with two different convergence criteria, but the same graph, it would have to convert that graph twice. It seems like caching that conversion makes sense, but obviously caching needs to be done thoughtfully so you don't run out of memory. Lazy IO operations. Normally, most graphs that you're going to use, you load from disk, either a CSV or some matrix market format, or pulled from a database. And so if you load that into a NetworkX graph first, and then are going to translate it to some other format, can we skip the NetworkX immediately? If we lazy load and just have that as a delayed task, and then decide, all right, I'm going to run this against cuGraph. Does cuGraph have a way to read that CSV file directly, for instance, or does GraphBLAS algorithms? So more ways to, again, get better improvements. But of course, anytime we're doing this kind of magic stuff, if something goes wrong, the user really needs to know what path did NetworkX take? Did it use the normal implementation or one of these plugins? So we need really good debugging, logging, introspection, all those kind of things. So again, this is all future work, not started, but something that we want to do and would love help with. So some key takeaways from this. First of all, NetworkX is amazing. Yes, it may be slow, but it's still an amazing library with an amazing community, and we think it has a long way to go. We just want to speed it up. Dispatching can make it 100x or more faster. Really, we want Spider-Man just to catch a ride on that bullet train, and have lots of different options: planes, trains, whatever. A reminder though that the user still interacts with NetworkX, right? They just make a call to their friendly neighborhood Spider-Man. Spider-Man's the one that knows all the train schedules and all that stuff. You don't have to deal with that. It's still nice and easy. Spider-Man just goes faster. Of course, I work on GraphBLAS, so I got to put a plug in that if GraphBLAS sounded interesting, it's really elegant way to do graph problems. Come check it out. Come join our community. It's still a growing area. And lastly, I really hope that NetworkX can become the graph API for Python. Just like Python is the standard way of doing machine learning. I would love for Python to be what people reach for when they have a graph problem, rather than some other library. So a couple of calls to action at the end of this talk. First of all, if you're a NetworkX user, give it a try. NetworkX 3.0 will be releasing soon. Don't be afraid to reach for GraphBLAS algorithms or cuGraph or any other plugin that comes out in the future. Give it a try and enjoy the faster speed. If you are a graph library contributor, maybe in the past you sort of have looked down on NetworkX. You say, hey, I've got this awesome graph library. It runs circles around NetworkX. That's fine. That's fine. But NetworkX, Spider-Man's over here trying to give you a high five. Reach out and give him a high five back. Join the team. Together we can make everything better. NetworkX will ship work off to you and make more people aware of your library. Use it, and similarly, you can benefit the whole community. As a community of Python, we can make graphs more awesome. And lastly, we would love feedback from everyone. Dispatching is a very early concept. I've sort of mentioned some things I would like to see in dispatching 2.0, but really there's a whole multiverse of possibilities. And if you guys try it out and give feedback, you can shape what it becomes. So yeah, give it a try. And if you do want to try it out, again, this is in NetworkX 3.0. Unfortunately, today it's not yet mainline. So if you want to install it, you have to do pip install NetworkX -- pre, and that will get you the version that actually works. Install GraphBLAS and some optional dependency. There's the command to install GraphBLAS. And to do the conversion from NetworkX, it at least needs SciPy. You probably want pandas in there for a nice display. And then here is the GitHub site with a little dispatch example to kind of dip your feet in. So with that, I will end and ask if anyone has questions.
What perfect timing. I was just popping on. It does not look like we have any questions coming in yet, but we'll give people a couple minutes. If anybody that is watching has any questions, please drop those in the comments. And Jim and Eric, I know, would be very happy to answer anything you have.
Yep, we're happy to talk about, NetworkX dispatching or just GraphBLAS or cuGraph, any of that stuff.
And if nobody does have any questions, we can, Jim and Eric can continue the conversation in Discord. You all can drop your presentation in Discord as well. If you want to provide your slides for folks that might want to go back and reference, or will be watching this at a later time.
Okay.
And I don't see any comments coming in. Oh, here's one. Can you see that there on the screen?
Compiled on M1. Yes. So I should note the Conda packages should work on every platform. They should work on Windows, Mac M1. The pip packages, we need to do a little bit of work for GraphBLAS. It's having issues on Windows and Mac ARM. So, but if you do install with Conda,